We had this problem with
with both
PowerPoint.
the Mac laptops.
Yeah.
Okay.
Okay.
Okay. All right, let's get started. My name is Sanjeev Satheesh. I'm currently leading the speech team at Baidu Silicon Valley AI Lab. At Baidu SVAIL, we are building end-to-end models for speech recognition. This gives us a unique viewpoint on how the community as a whole working on end-to-end models using deep learning is evolving, and I'm here to share with you the story as we see it on how the community is evolving, what problems are being tackled, and what new problems might be tackled in the near future. But first, what are end-to-end models? Let's start from a model that's not end-to-end, right? Typically, rich, very hard machine learning problems like the automatic speech recognition task, where the task is given an input audio, your task is to provide what the person in the audio is trying to say in plain text. A complicated task like this typically used to be solved by breaking it up into smaller problems and smaller and easier problems. In this case, an easier problem is to first predict phonemes. Now, what are phonemes? Phonemes are an artifact to account for the complicated morphology of the English language. The problem is English language does not guarantee you that the same sound will be spelt the same way, nor does it guarantee that the same spelling is associated with the same sound. Phonemes make the guarantee available to the systems so that a phoneme will always map to the same sound and a certain set of sounds will always map to the same phoneme. So that makes it an easier problem to solve. First, you solve the task of mapping from sounds to phonemes, and then you push the problem later to solve the task of going from phonemes to plain text. This involves multiple machine learning models. An end-to-end system, on the other hand, does not make hand-engineered assumptions like this. It tries to go directly from waveforms or spectrograms, if possible, directly to plain text or characters or words in the final language, or in the language you care about. The entire workflow of multiple machine learning models in the earlier workflow is replaced by a single deep neural network that is trained end-to-end, in the one end being the audio, the other end being plain text, right? So this is more end-to-end than the model that we saw before, which had multiple machine learning models that are sewn together and sometimes trained together, sometimes trained independently. So you would call this as more end-to-end than the previous model. Here are some tasks that are recently solved by end-to-end models using deep learning. Of course, the first thing that got a lot of press coverage was the object recognition task. Maybe 6 years ago, we could not even recognize with a 90% accuracy what is the object that is in an image. And sometime in 2012, 2013, we found out that by training a single convolutional neural network that takes an image and directly predicts the class of the object in the image, we're able to solve the problem very well so that we are at over 90% accuracy. Now, this also enabled us to solve more problems. We are now no longer just trying to solve the object recognition task. We are also trying to solve image captioning, which is trying to describe the image in a small paragraph. Not only saying, here's a cat, the task is now to say, the cat sits on a mat in a garden or whatever. So end-to-end models not only enabled us to solve certain tasks, but it also opened up new tasks that are available for us to solve. But why? How did this happen, right? That's the question. Before end-to-end learning and before deep learning, people used to work on a fixed data set, which is or a bunch of different data sets which are roughly about the same size. Let's say one may be 1 or 2 orders of magnitude bigger than others. And the way you would make progress on this data set would be by making better modeling assumptions. For example, in the speech recognition task, this would mean instead of trying to predict phonemes, you try to predict a triphone state, which gives more fine-grained control on what you're trying to model. By giving more fine-grained control to the modeler, we are able to solve the problem better. And so the situation would look like this. From ML workflow 1, you would go to the ML workflow 2, and at the first orange line, you will see an improvement in performance. The insight that led to the advancement of end-to-end and deep learning methods is finding out that if you were to take a sufficiently expressive model and throw tons and tons and tons of data at it, then it will make the best modeling assumptions it needs to model the data as well as it could. So what happens is, if you are able to find a model that's a few orders of magnitude bigger, you'll go to the other orange line and find that a sufficiently expressive model that you manually are no longer making any assumptions will make all the assumptions for you and model your data better and will improve your final metric. Of course, this also means that you will need a lot of data. Clearly, in the first case, because the model has fewer hand engineering knowledge about the task, it will underperform traditional workflows like the ML workflow 1 and ML workflow 2 because it'll typically overfit the small data set, right? But if you are able to find more and more and more data, you will find out that a sufficiently expressive model will do better than any hand-engineered pipeline. So directly optimizing the metric you care about is, of course, the #1 reason for the advancement of end-to-end models and deep learning. But there are others. One thing is that it is easier to obtain data for it. Let's look at the speech recognition task again. If you were to build a speech recognition system that is trying to predict phonemes, you will need label training data that is labeled in phonemes. And it's significantly harder to find people who can spell sounds for you in phonemes than to find people who will spell sounds for you in plain English or plain Chinese or whatever language you're trying to work on. So it's significantly easier to obtain a larger amount of data than traditional systems that's using hand engineering. Another example of this is in mission translation. Earlier, traditional mission translation systems not only needed parallel corpora between a source language and a target language, but also sometimes needed an alignment information that mapped these words in this sentence, in the source sentence, to those words in the target sentence. And these alignments are significantly more expensive to obtain. Now, with the advancement of neural mission translation that is training a single neural net to go from a source language to a target language, it's significantly easier for you to get more data because you no longer need to get alignment information. The other half is also a people problem, in that it is easier on practitioners. How is it easier on practitioners, and why is that interesting? Earlier, if you go back to the earlier model, right, you would need to code, build, and maintain a Gaussian mixture model, code, build, and maintain a hidden Markov model, and code, build, and maintain a plain text language model or a finite state transducer or whatever it is you're using. But if you were to replace the whole workflow with a single deep net, you now no longer have to code, build, and maintain all these different things. It's a significantly simpler workflow. And now there are more awesome toolkits like TensorFlow, MXNet, and all the other toolkits that are available that makes it easier for you to build a workflow and deploy it and maintain it. The other half of it being easier on practitioners is this. So you guys saw from the previous talk, for example, that there was crosstalk between the speech domain and the vision, people working on the vision domain. This is fairly unheard of. People working on finite state transducers normally never look at computer vision tasks or go to the computer vision conferences or learn about computer vision tasks, because it's highly unlikely that things will transfer. Now things are transferring. It's easy for you to take a CTC loss function that you have been using for speech recognition and now apply it on a computer vision task, because things transfer across domains. This has the side effect that there are more people working on problems that you are interested in. And that's important for this reason. The way machine learning models are built and improved and developed is by this flywheel. People come up with an idea, and somebody has to write it up and then run experiments to find results. And from the results, you gain some insights that gives you further ideas on how to improve the model. If you have more people working on the same problem and a lot of crosstalk between people working on different domains, that's more people working on the last arrow and the first arrow. That is, there are more sources of ideas and more people interpreting results for you. So that helps to make the flywheel go faster. All this simplification also has the other side effect that now there are more people. All the simplification now leads to more people working on AI and machine learning. If you just look at the Reddit machine learning channel, all the top voted comments, all the top voted posts are from the past 1 or 2 years. This is interesting because I think it is saying that things are a lot more accessible to people than it was before. And the best example is this. Well, maybe not the best example. One cool example is this. So in our team, we are working on building speech recognition systems that is trying to transcribe both English and Chinese. So at the end of a year, we had built a reasonably good English speech recognition system, and we were curious, would it transfer to Mandarin? Would we be able to take this model and apply it to Mandarin? In traditional systems, this would be fairly impossible, because you would need to have a person who knows the language to know what modeling assumptions to make to build a speech recognition system. Here, since we are not making any modeling assumptions other than we are making a smaller set of modeling assumptions, we were able to take pretty much the same model and apply it simply to the Mandarin data set and do pretty well on it. Not only that, we found insights from training Mandarin models that we later took and applied it to training English models. You can see this in the Deep Speech 2 paper where we talk about sortograph. All right, the other half is challenges. The same thing that was good for deep learning is also the difficult side of it, in the sense that you need to find lots of training data. So for example, if you are trying to build AlphaGo, for instance, right? It's impossible for you to find more examples than all the recorded games that people have online. If you're trying to build an end-to-end model for controlling a robot, it's impossible for you to get more than 100 hours per week on a robot. So does this mean that end-to-end models or deep learning on these tasks will not work? As we saw from the previous talk, people can get really creative and start generating synthetic data sets that look very close to the real thing. AlphaGo, a big part of AlphaGo's remarkable victory is that AlphaGo improved by playing against itself. It generated more games for it to train on. Similarly, for robotics, people are trying to build simulators so that you can do a lot of training on the simulators and then try to transfer out of the simulators. But this will be a challenge. If you are trying to build an end-to-end deep learning system, you always have to keep thinking about your source of data. The other half is that you need to find lots of compute to explore architectures. What does this mean? For instance, for training a deep speech model, that is the speech recognition system we are building, it needs about 20 exaflops of compute over 3 weeks, let's say. 20 exaflops is 2 followed by 18 zeros. And that's a ridiculously large amount of compute. And that's important because the compute is what is powering your second arrow to go from code to results. What happens between code and results is you training a model and waiting for your model to train. If you don't have a lot of compute, that part of the second arrow will become your bottleneck. And so it's really important for us to have super fast compute. Thankfully, we can outsource this to NVIDIA and Intel. If NVIDIA's talks are to be believed, we are expecting a 1,000x improvement in performance by 2025. The last thing is that you also need lots of compute for deployment. Typically, people have been serving linear models for solving various machine learning tasks. So for example, when you're making a search query on Google, there's a whole bunch of linear models going out, maybe not now, a few years ago. There's a whole bunch of linear models out there that are trying to predict which advertisements are most appropriate for this query, or which search result is most appropriate for this query. Those are nice to deploy because there's very little compute in it compared to today's deep neural networks that have lots and lots of compute in it. Can you do all of that compute within the 100 millisecond latency that constrains web search queries? That's the question. We think we can solve this problem with batch dispatch on GPUs. GPUs are really good at throughput. This means that they can get a lot done in a short amount of time, but they're not good at latency constrained task, which is if you want a small amount of stuff done in a small amount of time, GPUs are not good for it, are not the best for it, let's say. With batch dispatch, what we are trying to do is to batch all the queries that occur at about the same time so that we can send more compute to the GPUs where they are in the regime where they excel the best. All right, so we looked at why end-to-end deep learning models and what are the challenges. So what do we think is coming up next immediately? Speech recognition, you've all seen from all the talks recently. It's almost here. I think that's fair to say. Speech synthesis is also almost here. Semantic understanding, I believe, is also almost here in the sense that it won't understand in the sense that how a human understands when you say something, but a task-specific understanding of what you just said is almost here. That is, you can train an end-to-end model for a specific task that goes from natural language to whatever task you want to do. So this will enable more natural interfaces. In general, more perceptual tasks, that is processing audio and processing images, making images more sharper by super resolution, all of these tasks are almost nearly here and available to people to use on their phones, on their machines. What's coming up next, maybe over the next 2 to 5 years? These are a little bit harder for us to predict. I kind of outline here a bunch of approaches that people are taking, and it's up to you to see if the tasks you're working on fit into any of these criteria. Composition of end-to-end models. So for example, you can take a vision system that is trained on a large amount of images, and then you can take a language model that is trained on a large amount of text and then compose them together to go from images to text directly. This is one of the early examples. You can also take a vision system that's trained on in simulation and go and take it and apply it on robotics, where you go directly from, by composing these two models, you can now take a computer vision model and apply it to work on robotics tasks. Super personalization. This will most likely be an effect of the compute going to the edge. Right now, all the compute is happening in the cloud. As you push more and more compute into your phones, into your laptops, you will be able to build and use models that are super personalized for you. There are very early trends showing that that there are models that are able to learn by interaction. And then there are also tasks that we are not solving because there's not enough compute. If you see a paper and you're like, oh, there's this 1,000x more compute than I can do currently, remember by 2025, you will get 1,000x more improvement in performance from GPUs. What's probably not coming, and what's probably not coming as an end-to-end model is autonomous driving and general dialogue systems, for instance. Simply because general dialogue systems, for instance, are a fairly ill-defined problem. So this means that it's going to be very hard for you to find and build data sets that try to solve this problem. Also, I don't think we have yet figured out all the components that are required to build a reasonable general dialogue system. Autonomous driving. This is end-to-end models for autonomous driving is a little bit tricky. You can look at the speech recognition task, for instance. We would say that the speech recognition task is about 95% solved. But that's not the kind of accuracy we want for autonomous driving. We want it to be 99.9999%, right? And speech recognition, people have been working on speech recognition for about 30 years. So it's a little hard for us to jump from where we are now and seeing an end-to-end model deployed in an autonomous driving situation. Well, that's all I have. So we went over what are end-to-end models, why are they so interesting, what challenges are we seeing in the future. Thank you. It says I have 2 minutes. If you have questions, yeah, please.
So is there any advantage of having end-to-end model by combining acoustic and language models? Because even though there's disadvantage, you have to retrain the network for when the acoustic context changes, right?
Yes.
Why not have a chain of 2 models?
Yes, you're spot on. Watch out for papers from our group that is basically trying to do that.
Can you repeat what you said?
So his question was, why not train an acoustic model and a language model together? Yes, sir.
One of your slides, you mentioned that semantic understanding is almost here. I'm curious to see where the sort of concrete things that you're seeing that gives you this opportunity.
Yeah. So the semantic parsing task, there was let's take a look at yesterday's announcement from Google Docs, where you can say, chart me this, and it'll give you a chart of A, B, and C, where your command is in natural language, not in SQL or the specific Excel formula. So this is, I think, an application of semantic parsing. You go from natural language to a language that the system can understand. So this is kind of an instance of what I'm saying as semantic understanding. It doesn't mean that machines will understand your natural language the way other people do, but for specific tasks, you will be able to find enough data sets and build reasonable models that go from natural language to API calls.
And your extrapolation is still based on the same architecture of deep network?
Yes, you should be able to build an end-to-end model that does this, yes. Yes.
What if you had labeled intermediate feedback such as phonemes? What would your advice be if you wanted the top accuracy and we had large amounts of data? Would you recommend abandoning the intermediate feedback completely and building, striving for an end-to-end model? Or have you ever heard of somebody take
I see. So
Your advice?
I think that depends on a case-by-case basis. So if you're trying to solve a narrow task where you don't need to solve this ultimate most general task of speech recognition under all domains, under all constraints, if that is not your task, then it seems more likely that you can build a specific system with all the hand engineering to solve your particular task. If you're more interested in solving the most general task possible under that should work under all constraints, then you're better off letting your model learn from data as much as possible. Yes?
You mentioned large data sets required to end-to-end speech recognition.
Yes.
How large the data set need to be common and what does it look like?
Sure. So for our case, our systems, based on the papers we published in December 2015, had about 12,000 hours of speech for English. Since then, we understand, just like how compute is important, data is also important. We have been growing our data sets since then. So let's say if you want to build a robust speech recognition system, a few tens of millions of data items with at least 10,000 hours of speech is a really good starting point.
Thank you so much.